All right, friends and neighbors, welcome back. I'm back from traveling, and then I realized that we did not do the Did I Know This Already questions from chapter 15. And in looking at them, they're actually kind of tough. And so I thought I would work through them as actual problems for you rather than just giving you the answers. So without further ado, we'll do this, and then we'll take a look at what we're going to do in chapter 16. So in this video, we're going to do the chapter 15, Did You or Did I Know This Already? And remember that the exam topic that we've been examining for the last couple of videos, it seems like, is the IPv4 addressing and subnetting. But of course, this is going to roll into what's coming up, which is routing. So in this one, we're going to do some analysis and some actual problem solving. And, I thought they were kind of tough problems, so I think it's worth working through. And then the chapter 16 look ahead, and we're starting a new section in the book. We're on to part 5. So did you know this already? So we have a class B network, 172.23.0.0. We need 100 subnets with the largest needing 500 hosts. Okay, so we got a class B, we need 100 subnets, and we got 500 hosts in the largest one. We also need to accommodate for 50% growth. That's a lot of growth with a single mask. That means that all the subnets will use the same CIDR notation, whatever it is, /27, /19, whatever it is, they're all going to be the same. How many masks, in other words, how many different subnet masks could you apply to all the subnets to meet this requirement? The answer is there aren't any. So let's see why that is. So I worked this out. Here's our problem, 172.23.0.0. We want 100 subnets and the largest subnet 500 hosts with 50% growth. Now, for at least 100 subnets in a class B, right, we could use a couple of masks that'll get away with it. Remember that if we want to create 100 subnets, right, we're going to steal bits into the host portion. So how many bits do we need to steal? Well, if we steal 1, that's 2 subnets. If we steal 3, that's 8 subnets. 4 is 16. 5 is 32. 6 is 64. We need to steal 7 bits so that we can create 128. Remember, we're doing this on powers of 2. So we need at least 7 bits. But 8 bits would also do it. 9 bits would do it. 10 bits. So there's a whole bunch of combinations that would give us 100 subnets. But the next requirement is that we need 500 hosts in the largest subnet, which means that we need a certain number of bits for this 500 host subnet. Well, how many bits do we need to have for 500 hosts? Well, 8 bits is 256, right? A full class C size address space. And so 8 bits gives us 256, so we need 9 bits to give us 512 possible. So that means that if we're just starting with a class B, then we go, okay, cool. I need 100 subnets, so I need at least 7 bits. All right, and then for 500 hosts, I need at least 9. 7 plus 9, I'm at 16. That sounds pretty good, except, well, we got to account for that growth. So the 50% growth means that we actually need 750 possible in that largest subnet. And if we were growing our subnet numbers, we'd need 150 subnets. And so, if we start off with, okay, we had 9 bits, now we need 10 bits for hosts, well, we don't have enough for the subnets. And so the answer here is that there's no answer to this particular problem. Question number 2, subnetting design. Okay, 200 subnets. We know what we're going to do then. 120 hosts per subnet, a little more reasonable. 20% growth, also a little more reasonable. Which of the following answers will work? And so there were 4, you had to pick one. And the answer was choice B, the 10 net with a /22 CIDR notation or a /22 subnetting. So let's take a look at that one. All right, so the thing that's going to get us is the growth thing. So 200 subnets and 120 hosts per subnet with 20% growth means that in the end, you'll need about 240 subnets and 154 hosts per subnet. So 240 subnets, well, let's see how we figure that out. Well, if we did 7 bits, like in the last problem, That would be 128. So we need 8 bits so that we can create all of our subnets. Now for 154 hosts, well, let's see. If we started off with 120 and did 7 bits, that would be fine. But of course, our growth gives us 8 bits for hosts. And so if we take a look at all of these answers, right, this slash 25, well, the slash 25, that's actually only 7 bits for hosts, so that's not going to work. This other one down here, slash 23, that looks like it's got enough room for the hosts, but does it have enough room for the subnets? And it turns out it doesn't because it's a class B. And a slash 23 would be 7 bits for subnets. And this bottom one here doesn't make any sense. That's just a class full address space, and that's not even doing subnetting. So the only one answer that works is the 10net with a slash 22. Why? Because we are creating a lot of subnets, right? That is 14 bits taken for the address space for all of the subnets, and you've got 10 bits for the host. So plenty of room for all of those subnets. So question number 3, the class B network of 172.19. So again, a class B with a single subnet mask. So everybody's going to use the same mask again. Choose the mask that provides the highest number of hosts per subnet while supporting 1,000 subnets. 1,000 subnets. This is a big number, but we can do this. So it turns out the slash 26 will do it for us, but let's see why that is. Now in this particular problem, and for most, I think, I like to occasionally break things out into binary so we see what we're dealing with. Now when I need 1,000 subnets, right? If I take 8 bits for the subnets, that's not going to do it. That's 256. 9 bits gives me 512 subnets, so I need 10 bits so I can get 1024. So this is the mask that I will have. That mask right there, at a minimum, is going to be, well, 26. So we got 8, 16, 24, and then 26. Now, one of the other things you can do is they're being a little tricky here, and they're saying, well, what is, we've got all these different mask types in the notation. So maybe what we could do is we could say, well, what is this one? This one's actually slash 24, right? And what is this one? Well, 255, 255, 255, 192. And this one down here is going to be 8 plus 8 plus 6. So that'll be slash 22. And slash 28, well, that's 8 plus 8 plus 8 plus 4. So this would be 255, 255, 255. And what's 4? 128, 192, 224, 240. And sometimes it's nice to do that just so that you can say, well, I understand the nomenclature, and I'm not trying to figure out what, all the different formats for each particular answer. But the real meat and potatoes here is understanding how many bits we need for the subnets. So when we take 10 bits for the subnets, we have 6 left over, and that would give us 64 possible hosts per subnet. Okay, question number 4, another class B network with a slash 22 mask. Okay, so we know what that looks like. When listing the subnets in order, which of the following would be true? So the thing to do here is to say, all right, if I was going to write them all out, what would be the patterns? And so that's what this question is asking about. Now, it turns out that the answers were C and D, the 64 possible subnets, and the last subnet was 172.32.52. But let's see how that works out. And it's helpful to write it all down and see what we're dealing with, right? It's just like a word problem that you used to do in math. So if we break this out into binary, and we're given the slash 22, well, that's just 8 plus 8 plus 6 more. So this is what the mask looks like. So that right there is the bits stolen. And we just ask ourselves, how many subnets did we just create? Well, 6 bits in a class B. Well, 6 bits stolen, no matter what network you're in, you're going to create 64 subnets. But now we also know, because it's a class B, the size of each subnet, which would be 10 bits of addressing for the host. So we create 64 subnets. We know that that's one of the answers. But what would the subnets be? Well, We could write them all down, but there are 64 of them, so maybe there's a faster way or a pattern that we can notice. So if we write down the first subnet, right, and we begin with the class full address space, and then we say, well, if I put the highest possible number, well, I suppose you do it up here. If I put the highest possible number right there with all zeros right there, then it would be 3.255. That would be my range. Another way to do that would be to convert 1023 to binary and put that in there. But whatever way makes sense to you, right? We've done a couple of ways. That would be our first subnet. Well, what's the next subnet? 172.34.0. Okay, so that pattern would be 0.000000100. Then we fill in all ones to get the highest. Well, it turns out that that would be 172.37.255. Now, if I'm looking right here, I say, okay, well, I added 4. Let's see if it works out again. Well, 172.38.0 is the next subnet, goes to 172.30.11.255. I go, oh, okay, all right. Well, that looks like a pattern. So I could just do all of the numbers that are multiples of 4. So you could do that. Now it also works out that in this particular case, right, in that octet, 256 possible values divided by 64 is 4. But we can also work backwards. We can say, all right, if this is the highest value that was there, and we know what was going on here, right? If I said, well, this value was 1 less, and then I just subtracted 3 from that, then I would get 252 as the highest, and then I could get, the next one down just to do some checks. So there's some patterns that you can look at, some shortcuts, but you sort of have to know what you're looking at. But those were the two answers, right? So this was the highest subnet, and we created 64 possible subnets because we stole 6 bits. Question number 5, which of the following are valid subnet IDs for a private network 192.168.9.0 using a /29 if this is used throughout, meaning the mask, the /29? Well, the answer was 9.144. So let's figure out why that is. Then again, we rewrite the question. And now this is a class C. So we're only dealing with 1 octet's worth of space. And we know that this is a /29. So we start off with a /24. So that's 5 bits of addressing for subnets. So we created 32 subnets. And we could write them all down again. Or again, we could try to look for patterns. Now we know that if I stole 5 bits for subnets, then I've got 3 bits left over for hosts. So I've got 8 possible addresses in the hosts. And in the first one, for example, it would be 0 to 7. If we wrote down what that first subnet might be, and then we just sort of did a little calculation here, then we would say, okay, the first one is 192.168.9.0, and we know that there's 8 possible. We start counting at 0, so it's 9.7. The next subnet up would just be one more than this one, so 192.168.9.8. We'll add 7 to that, and we go 192.168.9.15. We'll do one more to have the pattern emerge, and we get 192.168.9.16. Okay, so we have clear multiples of 8. And so the shortcut here is, are any of those answers divisible by 8, or do any of them, are any of them just crazy outside of what was there? And so the only one that fits is 192.168.9.144 because 8 goes into 144 evenly. Question number 6, which of the following is not a valid subnet ID for private network 172.19.0.0 using a /24 if this is used throughout? So again, everybody's using the same mask. A lot of these problems are same mask problems. Well, the only one that doesn't make any sense whatsoever is 172.19.0.16. And the reason it doesn't is because while there's a 0 here and you go, well, wait a minute, if we start with a class full address space, wouldn't I start there? And the answer is yes, but it would be all zeros everywhere. And so that .16 doesn't make any sense. But again, we'll take a look. Now, the cool thing about this problem is that it's a /24. So that means the entire third octet is where all the action is. This is where all of the subnetting happens. So there should be nothing going on in the last octet. There will only be two values there. The lowest will always be 0, right? No matter what the subnet is, that it'll say .0 for the subnet address. And no matter what's happening, it'll be .255 in the last octet for the broadcast. We just have to figure out the third octet. Well, if it's in the third octet and we're just counting through that, then we start at the class full address space and then we just go the 1 net, the 2 net, the 3 net, and so on. So the first subnet is 172.19.00, and the range of addresses goes up to 0.255. We add 1 and we get the next subnet, 172.19.1.0, all the way up to 172.19.1.255. It's really, really straightforward. And so it will go through all 256 possibilities to get the subnets, and they would all just be numbered according to what was going on in the third octet. So all you had to do was figure out which ones don't fit that model, and the one that didn't was that silly .16 in the last octet. All right, we'll close out or get ready to close out with some subnetting fun facts and some foreshadowing. Obviously, with these problems, these were a bit challenging, I thought anyway, and so you got to remember your binary and your powers of 2. They will save you more times than I can say. In addition, most of the examples so far focus on a single mask used throughout. So all of the subnets are the same size, they all use the same mask or the same CIDR notation, and that is where we always start with subnetting. Now this indicates that sometimes we use different masks within the same organization or within the same set of networks. So it is very possible to take a whole bunch of subnets and make them equal size, and then take one of those subnets and make it, well, glued with another one to increase a chunk of the address space. Or you can take a subnet and further chop it up into smaller and smaller subnets. When we do this, that's called variable length subnet masks, or VLSM. Another fun fact, normally we think of the smallest subnet that's possible as having at least a couple of addresses for nodes. So for example, a very small subnet would be 192.168.1.255 to 250, or 1.252, and the range would be 255. So the mask would be 255, 255, 255, 252. That only gives us 4 addresses, right? Because there's only, when you do .52 or when you do .252 in the last octet, there's only 2 bits left for hosts. So you say the subnet ID, the broadcast ID, and then 2 addresses for host, and one of them is going to be a router. But there's a whole RFC dedicated to allowing /31, only 2 addresses for a particular subnet. So RFC 3021 using 31-bit prefixes on an IPv4 point-to-point links, because there are no hosts. So that's where you can get away with it. If we can subnet, we can also supernet, which means we glue subnets or networks together. So if we started with a class C and we needed more address space, or we wanted to simplify routing tables, we might glue a class C network address space with another class C address space. That doubles the address space size, but it also reduces the number of addresses in a routing table. We'll do that later, but just a little foreshadowing. There's a whole bunch of stuff that we do with masks when we get a little more advanced and we get really good at this stuff. The chapter 16 look at, remember we're starting part 5 now. It's very exciting. So the network fundamentals will be IPv4 addressing and subnetting, but we're going to look at routers, right? So that's what we're going to do. We're going to take a look at some chassis, the interfaces, learn our way around them, right? Just like we did with switches, do some statistics and see how things work. So I'm fairly jazzed about looking at routers and moving up to layer 3. So this has been subnet design. I feel like we've been doing subnetting problems for weeks. It's probably because we have. But this was working through some tough problems. but I can't wait for routing. You're going to have a ball. This will be fun. All right. So if you enjoyed going through the subnetting problems, or at least were happy that I went through them, like and subscribe. Thanks for watching. Thanks for listening. May those packets always reach their destinations. And remember, this is CCNA. You can do this.